Swayam Prabha. Digital India. Educated India.
Welcome back. So, today let us begin with our discussion of single phase rotating machine. Our idea is actually to do 3-phase synchronous generator or 3-phase rotating machine and 3-phase induction generator and motor, but we will start from single phase rotating machine, take baby steps, first do single phase rotating machine, then do 2-phase rotating machine, then bring it up to the 3-phase rotating machine. The reason being, single phase rotating machine we need to worry with only 2 windings, 2-phase rotating machine we will have to worry with 4 windings, and finally for 3-phase rotating machine we will have to work with 6 windings. So, it is better to start from 2 windings, do the math there, then go to 2-phase machine, do the math there, and then finally reach the 3-phase machine, which will have 6 windings in total. So, earlier if you recall, we have shown that when you have concentrated windings on the stator and rotor, we had developed the inductance formulae for self inductance and mutual inductance and the flux linking the stator winding and the flux linking the rotor winding. So, I am just recalling that here, and that is Ns square L0 Is plus Ns Nr L naught 1 minus 2 theta by pi times of IR, and the lambda r, the flux linking the rotor winding is NO, I am sorry, Ns Nr L naught 1 minus 2 theta by pi times, here it is Is, here this is the self inductance times the its own current, mutual inductance times the current in the other winding. Now, here we are calculating flux linkage in the rotor winding, this place we were calculating the flux linkage in the stator winding. So, when you are calculating the flux linkage in the rotor winding, mutual coupling is with respect to the current in the stator winding, and the mutual coupling is essentially the same, that we know that this is A to B, B to A, S to R, R to S, the mutual coupling is same. We have derived these formulas earlier, and Nr square L naught I R. So, this term is, this side is rotor winding flux linkage, this side is rotor winding current. So, therefore, this indicates the self inductance of the mutual self inductance of the rotor winding. And if you recall, n square by r, where r is the reluctance, or n square P, where P is the permeance of the magnetic circuit. If you recall this as our derivation of the inductance sometime back, then you would realize that because the geometry, and I am going to draw the figure, do not worry about that, because the geometry we are taking iron as an ideal element. So, rotor, inside the rotor, the flux lines to pass does not require any MMF or effort. Inside the stator, it does not require any MMF or effort. Only effort is required in the air gap. So, and the flux linking starts from the, whether the winding is on the stator or on the rotor, the flux will always start, will pass from rotor to the air gap, through the stator, back through the air gap, and again close the circuit. So, the geometry shared is essentially the same. So, therefore, that geometry leads to a permeance of L naught or L naught, so to say, essentially this thing, and Ns is the number of turns on the primary. So, Ns square L naught becomes the self inductance of the stator, Nr square L naught becomes the self inductance of the rotor, and the mutual inductance becomes Ns Nr L naught into 1 minus 2 theta by pi. The 1 minus 2 theta by pi is basically because it is geometry dependent. When it is aligned, theta is 0, then it is exactly Ns Nr L naught. When theta becomes pi, it exactly reverses. So, you get minus 2 pi by pi. So, therefore, minus 1. So, the mutual inductance, when you rotate, something is aligned, stator and rotor are magnetic axes are aligned, you get the maximum maximum at theta equal to 0, you get the maximum mutual coupling. Then when you rotate the rotor by 180 degree, it is exactly opposite. So, the dots polarities, everything undergo a 180 degree change. So, therefore, it changes its sign to minus of Ns Nr L naught. That is why this term of 2 theta by pi had come, if you remember that from our earlier discussion. And so, this we had sketched that this is therefore a linear term like this as a function of theta, it goes with a double frequency oscillation, we had seen this earlier. And so, the point which I am trying to sort of make out is, this is something we know, but this is with concentrated windings. What we usually do is, we want to, when you look at this kind of a triangular kind of a waveform, again when you do a Fourier analysis, you will get a fundamental component and harmonic component. Now, harmonic components of the fluxes will create harmonic voltages, which we do not want to have. So, what we do, and I think I have done this earlier also, what we do is, we distribute the winding. So, let us say this is my so let us say this is let me increase this, air gap is too big, uncomfortably big air gap. No, this is okay. So, what do I have here? This is stator. What do I have here? This is rotor. And what do I have here? All this here. This is my this is my air gap, right. Now, what we do is, we distribute the winding. So, we put slots here, let us say in the stator. Actually, I am showing it, we should not show it outside, actually it is the other way around. I cut it like this. I cut it like this, and let us say the dots are here, that means current is coming out of the windings here, and current is going inside from top to down here. So, current comes out, overhang, there is no magnetic flux layer, just a connector, then goes down, then from below connects back, like this, like this, like this, like this, it is going, but it is no more concentrated, we have distributed the winding. So, when we distribute the winding, and there is a technique to it, how many slots, how many conductors per slot, all that when you properly take care of that, and we have seen part of it, if you recall, we have seen that part of it. I instead of this I will put the slots. So, this is the axis, magnetic axis of stator. This will not change because stator winding is not rotating, but magnetic axis of the rotor I am going to draw it at some angle here. The figure are not up to mark, but it is okay. We are only doing a depiction. So, now this is the magnetic axis of the rotor, and anti-clockwise direction is taken as the positive direction. It is at an angle theta with respect to stator. This theta can change because the rotor winding is going to rotate. So, because the rotor winding is going to rotate, it can be here. Now, by doing this, what we make sure is, instead of having this as ns nr L naught into 1 minus 2 theta by pi, we create this mutual inductance as this times of cos of theta, or in other words m cos of theta. So, I had said something about double frequency here, that is not correct, single frequency only, but now it is no more linear, it's no more, it's single frequency, because at pi the m inductance becomes at pi angle minus m, and then at plus angle again it becomes 2 m. So, it is actually it was like, I am sorry. So, you had plus m minus m plus m, but it was going like this. We did not want this. What we want is a smooth variation, sinusoidal smooth variation like this. So, therefore, m cos theta. So, it peaks up here at becomes pi becomes minus m, and again reaches plus m at 2 pi, and if you keep going on like that. So, by proper distribution of the windings across the stator and the rotor, we in practical machines ascertain that the mutual inductance becomes m cos theta. As a consequence, now the equation for the flux linking the stator winding would be given by LSIS plus LSR of theta, mutual inductance. I will directly write it as m cos theta times of IR, and the flux linking the rotor is going to be m cos theta IR plus the term which comes out of self inductance, which is LR IR, and I am sorry, mutual, first term here is the mutual coupling, it should come with respect to the stator current. So, m cos theta times of IS. You could always write it in the matrix form also. I do not need matrix form, but I just want you to see how the structure 2 by 2 block comes. IR, I am sorry, IS and IR. This is the, this would be the depiction of this would be the 2 by 2 representation of the matrix representation of the flux linkages. Now, okay, one way to also show this is to show a coil like this here with plus minus IS Vs. This is the stator axis, magnetic axis of the stator. magnetic axis of stator, and this is the magnetic axis of rotor, angle of theta. You apply VR here and the current going through it IR. So, instead of showing all this distributed windings and so on, here for the sake of depiction they are shown as concentrated windings, but at an angle of theta. But remember, I mean they are not concentrated, but every time we cannot draw a distributed winding, you see. So, therefore, we resort to some such simple approximations. Now, if we want to understand what is the torque generated due to this interaction of the currents and the magnetic fields between these two, we have some exposure to speed EMF, we have some exposure to transformer EMF, some of those things we are having that exposure. So, what we have to write is, first thing is to calculate the co-energy of the system, and then step 1 is calculate Wm dash, the co-energy of the system, and then the step 2 will be to calculate the electromechanical torque as the positive rate of change of co-energy with respect to theta. In this case, I can write even d also, but there is only one, it is okay, there are 3 variables. So, it is okay to write partial derivative is, ir and theta, these are the 3 state variables that we are having. So, partial derivative of Wm dash with respect to theta. Now, how to calculate? So, you again recall that co-energy is path independent, being a conservative field. The calculation or the integral which is involved in calculating the is going to be path independent because of the conservative nature of the magnetic field. So, therefore, we could what we will usually do is we will have 3 axes, say theta, is and IR. This is just again another depiction. So, and IR. So, what we will do is, first we will keep IS 0, IR 0 and assemble it to the right level of theta. Then what we will do? We will increase, keeping IR 0, we will bring IS, I will call this as IS dash and IR dash. Dash here is just a dummy variable, because current finally I want to show it as IS. So, I will increase the stator current from 0 to IS, and then finally I will increase, now theta is also at its right position, current in the stator winding is also at its right position, and then I will increase the rotor current and bring it up to IR. So, then I would have assembled the system, and I will do the integration and calculate the co-energy as it is increasing across these components, and when I reach this place I would know the co-energy of the entire system. So, the first step, as you know, does not cause any, because it is a de-excited system and you are bringing the right topology. So, there is no integration to be done here. The integration is done in this step and the integration is done in this step. So, the integration which is done in the first step is lambda s, is dot, is dash, rotor current is 0, theta is at its original position, and I do a dis dash and I integrate this from 0 to is, 0 to is. So, this is the first term, which is the energy, co-energy which is accumulated when I go from here to here, and then after that the is is not changing. So, this term will not come into play, only the theta is also not changing, only thing that will change now is IR. So, the next integration will only have IR as its variable, and I will have this as 0 to IR and lambda r, the lambda r I s already set there, and IR dash being increased from 0 to IR theta d I r dash. So, the accumulation is keeping IR 0, first accumulation is done here, and then all the co-energy which is going to come due to this component has been taken care of. Then comes the, we have to take care of what happens due to this component, the second component here, and for that what we will do is we will increase the current from 0 to IR dir dash, and we will get the second component. So, this is the creating the component of the co-energy due to the stator winding, and this is the component which is going to come due to the this is the component which is going to come due to the flux linkage in the rotor winding. So, these two components are taken care of. Now, if you look at it here, because in the first term IR is set to 0, look at this, IR dash is set to 0. So, this term is not going to come into picture. So, whatever this is basically just LS I S, I am sorry, whatever this term is, first term is only LSIS, and when I integrate it with respect to LSIS dash integrated with respect to DIS dash will become half of LSIS dash square, half of, when I integrate this it will become half of LSIS dash square with limits from 0 to IS. So, therefore, the energy which is accumulated here is half of IS square, and the, now look at the second term. Now look at the second term. So, the when you integrate this, IS is now fixed to whatever, it has been brought to whatever level you wanted to bring the IS level, and you are going to integrate with respect to dir dash. So, you are integrating it with respect to dir dash, just look at the first component. So, what will happen, IR dash term will come here, and then you are increasing it from 0 to IR. So, therefore, what will be accumulated will be m cos theta IS IR, m cos theta IS IR, and when I integrate this, there is a dir dash sitting here, and I am integrating, LR being a constant. So, this will become half of LR IR square, and then integrating from 0 to IR dash square, then integrating from 0 to IR. So, therefore, the third term which will come will be I am sorry, will be half of LR IR square. So, you get Wm dash as half of Ls I square plus half of LR IR square plus m cos theta into IS IR. So, now you have accumulated the co-energy, right. Now, you have accumulated the co-energy. Now, you can calculate the torque, the electromechanical torque, as partial derivative of this with respect to theta. So, you need partial derivative because the state variables are IS, IR and theta. So, there are 3 state variables. So, you should not write it as D. I was almost about to make that mistake, but you should not do that mistake. And take the partial derivative with respect to theta, it is positive. Remember, co-energy we take a positive partial derivative. When you do it with respect to magnetic stored energy, then you take a negative partial derivative. Let us not worry about that, we have seen that. So, when I take the partial derivative with respect to theta, first term will not contribute anything, second term will not contribute anything, only the third term will contribute, and this will turn out to be m ISIR derivative of cos theta is with respect to theta is minus sin theta. So, therefore, this torque will be so many Newton meters in SI unit, the torque will be so many Newton meter. Now, let us say that let us say that the moment of inertia is J. Okay. Then let us write the electrical and the mechanical equations associated with this circuit. So, what I have here is what this box is my coupling field. Okay. Then I have two sets of coupled windings. This is just a depiction with the one is the stator winding with the resistance Rs, and I have applied a Vs to it. Other is similarly the rotor winding with the resistor Vr is applied and the resistance is Rr. The resistance is applied is Rr, and this side represents the mechanical part of it. So, you have plus minus, the variable of interest here is theta, and you have this moment of inertia block, the work gets done out of this. Then you have a damping block indicated by B, and then you have a spring block with spring constant K, and you have applied mechanical input as Tm. Actually, will come to that, actual is Tm. So, then what happens is total that gets applied is Te plus Tm. Actually, it is never like both, you do not apply both Te and Tm. In motor, the load is to be driven. So, Te and Tm will be opposite to each other. In generator, the Tm is applied and the work gets done on the when you have these lights glowing and all that kind of thing, this creates a so this creates a retarding torque which is Te. So, what I am trying to say is in writing generic equations, we are assuming as if both Te and Tm are applied, but in generator the Tm is applied in the direction of theta and the electromechanical torque comes as a retarding torque because of this all these electrical loads which are after electromechanical energy conversion, all these lights are glowing and the induction motors are working and your refrigerator is working and what not, all of this is creating a retarding torque Ta on the shaft. So, this is my generator, and in case of a motor it is the other way round. The load is the retarding mechanical torque, like for example, suppose you are trying to push something uphill, its tendency is to come down. So, that is the retardation, but you want to push it up. So, what you have to do is you have to apply Te in the direction of the rotation theta, and this gives you a motoring action. So, generator and motor will have Te and Tm always opposite, and when they cancel out to each other, then you will get a equilibrium position where the speed will become constant. So that but generic equation we can say, okay, I am applying T, I am applying Tm, and I can take care of the signs which is positive and which is negative when I am discussing generator and the motor. So when I am discussing motor, T is going to be positive, Tm is going to be negative. When I am discussing generator, Tm is going to be positive, T is going to be negative, that is all. So this becomes the applied and minus k times of theta. This is just similar to what you have in a spring, right. This is the rotational and this is the rotational analog of the spring. The spring, the force which is created is minus k times of x when the spring is elongated by x. The force which tries to bring it back is opposing force is minus k times of x. Here I am writing it for the equivalent rotor analog of it minus k theta, and the third term is going to be another term which tends to reduce or oppose is the term which is corresponding to the damping minus b d theta by dt. This is due to the friction, not friction, but the drag which when you try to rotate something in a viscous medium, what happens? The viscous medium opposes that, right. You try to rotate something in a viscous medium, the viscous medium opposes it, and that is, as a first principle, that is proportional to the velocity at which you are trying to rotate. More higher the velocity you want to rotate it, more opposing torque that it will create, and you will have to push that much extra torque to rotate it. So this is that component, and so this whole of this thing, this is the net torque which gets applied. What I show here is the net torque which gets applied, and this will cause the machine to accelerate with a speed omega which is j omega by dt. But omega is what? Actually I will write it as omega m, I will write it, the speed of rotation of the motor. Now theta is going to be omega m t plus, let us say, some gamma, where gamma is the original angle between the rotor axis and the stator axis, and now the rotor is rotating at a speed omega m. So rotor is rotating at the speed omega m. So the angle which will be created will be omega m t plus of gamma, and d theta by dt is going to be equal to this omega m, and so d omega m by dt will be d square theta by dt square. So this whole equation now, I can write it as write it as, I am sorry, this is troubling me. This is what I want. These two terms I can take it on left hand side. This I can substitute it by d square theta by dt square, and then this generic equation becomes j d square theta by dt square plus b d theta by dt plus of k theta equal to T e plus T m. So this is the mechanical equation. Now let us write the equations for the stator windings and the rotor windings. So stator, we are applying a voltage Vs, it in the stator winding has the resistance Rs. So it will create a drop of Rs Is, and then whatever is left will correspond to the voltage due to rate of change of flux linkages in the stator, which is d lambda s by dt. Similarly, you will have VR when you apply, it pushes a current IR, this pushes here the current pushed was IS. This in turn will create a drop of IR, RR into IR, and then whatever is left here is going to correspond with respect to d lambda r by dt. So, therefore, the we get Vs is equal to RSIS plus d lambda s by dt, Vr is equal to RRIR plus d lambda dr by dt, and the mechanical equation that we just have already derived, k times of theta is equal to Te plus Tm. These three equations describe the complete this single phase rotating machine. So, these describe the complete single phase rotation machine, the state space model. This is called the state space model for the rotating machine. Actually, for state space model we will want to write this as d omega by dt and then omega as d theta by dt. So, actually 4 state variables will come into picture. But anyway, state space model we write when we want to study the dynamics of the electrical machines, but before doing the dynamics of the electrical machine we have to study the steady state analysis of the machine. In the steady state analysis, basically what happens, the rotor speed becomes constant. When the rotor speed becomes constant, then that is called the steady state analysis. Most of our, when you run the fan, let us say when you start your fan, it accelerates, then it comes to a speed and keeps rotating, that is the steady state analysis. When it is at 0 speed and until it has come to its steady state speed, what is happening, that is the dynamic part of it. So, in the first course we do not want to get into the dynamic part of the rotating machine, we only want to see the static the steady state analysis is what we are interested in. Now, in case of synchronous machines and induction machines which we are interested there is only sinusoidal excitations that we need to worry, either DC currents or sinusoidal excitations. DC current is like saying that I am having something I of sine of omega t plus theta, but omega is 0. So, it becomes constant at I sine of theta. So, therefore, it is basically, in other words, in the study of synchronous and induction machines which is of interest to us, we are interested only in sinusoidal steady state. Therefore, we proceed to find conditions and then we will proceed to find conditions for average power transfer in that steady state condition. So, towards to that end let Is be equal to I capital S cos of omega s of t and IR be equal to capital of IR cos of omega r of t, and then let us look at what is going to be our TE. The TE that we had derived earlier was, let me pick it up from here, minus of m ISIR sin theta, is it not, minus of m ISIR of sin of theta. And so, I will write substituting this minus of m ISIR cos of omega s of theta, cos of omega r of theta and sin of theta, where theta is omega m t plus the original initial angle gamma. So, I can write T torque, electrical torque, electromechanical torque is like this. Now, what I will do is, this is cos A cos B. So, I will 2 cos A cos B is half of cos of A plus B plus cos of A minus B. So, I will write this as minus m ISIR by 2 cos of omega s plus omega r of t plus cos of omega s minus omega r of t times sin of theta. But the sin of theta again I will write it as this divided by substituting for sin of theta cos of omega s minus omega r of t times sin of omega m t plus gamma, omega m t plus gamma. Now, what I will do is this I will treat it as sin A, this I will treat it as cos of B. So, sin A cos B is half of sin of A plus B plus sin of A minus B. So, this is what I will use once with this and once with this combination. So, now another first cos of first this thing created two terms. Now, each one of them will further split into two more terms. So, finally, I will end up with 4 terms. So, I will get this as minus of is IR by 4. Why 4? Because when I am sin A cos B is half of sin of A plus B plus half of sin of A minus B. Again sin A, this time this as cos B is going to be again another half of sin of A plus B plus sin of A minus B. So, that half can be taken out further outside here, and that will give me a factor of finally a factor of 4. And then now let us first do the sin of A plus B here. So, that is going to be sin of omega m, A is omega m t plus B is omega s plus omega r of t, and there is that gamma still sitting there. So, plus of gamma, whole of this comes in one bracket. So, this becomes sin of A plus B plus sin of A minus B. So, I will directly now write it as omega m minus omega s minus omega r of t plus of gamma. You can see this here, right? I mean, you can see this here. This is A, this is B, and this is A minus B. You see that? Okay. Then we will proceed to this term. So, I will write this as again plus sin of A plus B. So, the A is here and the B is here. So, I will get this as omega m plus omega s minus of omega r of t plus of gamma plus A minus of B. So, sin of omega m, and then which is to be minused? This one is to be minused, and then finally gamma has to be added because A contains gamma also. So, I will write this as omega m minus omega s plus of omega r of t plus of gamma, and then this whole big bracket will close. So, now you have got 4 terms inside of this sign, and let us call omega 1 as omega m plus omega s minus omega r. So, which is the omega m omega 1 term? Omega 1 term is this one, omega m plus omega of s minus of omega of r, and let us call omega 2, because there are 4 frequency components. I am writing omega 1, omega 2, omega 3, omega 4 like that, omega m minus of omega s plus of omega r. So, this is basically this terms minus of omega s plus of omega r, and where is this term sitting here? this fourth one, omega m minus of omega s plus of omega r. So, this term I have called it as omega 2. So, let me write it, this one is going to be omega 1, this one is going to be omega 2, and now you can see where is the omega 3 and omega 4 coming into picture. So, this term here, the omega 3 is going to be omega m plus omega s plus omega r, and omega 4 is going to be omega m minus omega s minus of omega r. So, if you look at this is omega 3 and this is omega 4. So, we will get P m as minus, I am not P m, I am still at T m, the electromechanical torque, T m as, I will get T m as m minus of m I s I r sin of omega 1 t plus gamma plus sin of omega 2 t plus of gamma plus sin of omega 3 t plus of gamma plus sin of omega 4 t plus of gamma. Now, you know that sinusoids over average over a cycle is 0, but what we want is is that average work should get done. Okay. So, before average work gets done, let me also now write the expression for P m, which is the power, which is torque times the omega m, the speed. So, therefore, it will become minus of I s I r omega m into, this is what, this is the overall expression for the overall expression for P m. Now, we want average work to be done. If average work has to be done just with sines, it is not going to happen, because the average of a sine is always a 0. So, either omega 1 or omega 2 or omega 3 or omega 4 should be 0. If one of these omegas goes to 0, then what will happen? If suppose omega 1 goes to 0, then this term will just become sine of gamma. If omega 2 goes to 0, then this term will become only sine of gamma, and so on for the remaining 2 terms. So, any one term, at least one omega should go to 0, and usually as we will discuss synchronous machines and induction machines, what happens in our construction is that the omega 2 goes to 0, which is to say that omega m minus omega s plus of omega r goes to 0, which is to say that rotational speed or speed of rotation is exactly the difference of the stator excitation frequency and the rotor excitation frequency. So, if this is 50 hertz, this is 10 hertz, then our machine should be rotating at 40 hertz. When this happens, this is usually called as the frequency condition. This is usually called as the frequency condition. It is the second term which say omega 2 which goes to 0, and if this happens, the other 3 terms will not go to 0. So, they will not provide you any average torque, and so P m average is just going to be equal to minus of omega m I s I r m by 4, and the what is the, this omega 2 has gone to 0, omega 2 has gone to 0. So, you just get a term called sine of omega. sine of omega. So, this many watts of work gets done. So, this is your single phase machine. One example of the single phase machine is the fan. Now, the thing is you cannot just start with single phase. You need to create a rotating magnetic field, for which at least you need two phases. We will discuss rotating magnetic fields again in more detail later on, but by itself these are not self starting machines. So, if you open up the fan and see, actually you will see the single phase motor as we discussed here, but another winding is required, or the rotor winding or whatever, it has connected across a capacitor. So, capacitor voltage and inductor voltages can be made to have a phase difference of 90 degrees. I am anyway going to do the single phase two phase motor very next step. So, you will see that point, but I am just telling you a bit about at this point of time the fan which you see upstairs there in your home, everyday home. And so, you create first a two phase motor to start with by having capacitor creating exciting voltage of the capacitor exciting one winding and voltage of the inductor exciting one winding, so that it gets a 90 degree phase shift between the two, and that creates a rotating magnetic field which starts picking it up. Then the capacitor comes out of the story, and it becomes, once it picks up some speed picks up, then it can function as a according to the gamma that is set and all that, it can function as it is a single phase motor. The problem with single phase motor is going to be the pulsating torque. See, I just said omega 2 can be, if omega 2 or the frequency condition is satisfied or the omega 2 goes to 0, and then I get average power work done. But omega 1 is still not 0, omega 3 is still not 0, omega 4 is still not 0. So, those are going to create pulsating components on your power. These pulsating power components can be eliminated if we go to balanced to two phase or three phase machines. So, actually all our industrial workhorse are induction motors traditionally, those are three phase induction motors, and all our generators are traditionally three phase synchronous generators. So that you do not have this problem of instantaneous power and average power being different. We have seen all that earlier also when we did single phase and three phase circuits, we motivated ourselves from single phase to three phase circuits. So, I am not repeating myself, but this is now we are going to see this at the torque level, at the shaft level. We are going to we are seeing what we saw at a gross level earlier, we are now seeing it at the shaft level. I will stop here for this class, and two phase machines I will take up in the next class. Thank you.